Hi, I'm David. I work half-time for invertnet, pretty much all day, every day. And the other 40 hours of the week I spend here in the computer science department working for the Illinois Intel Parallelism Center. So I'm just going to kind of quickly go through all this stuff because I know we're all going to spend some time up with the hardware, near the hardware, fighting the hardware. But I'll give you the story of what we've done, how we got here, and where we're going to go. Keep in mind that the goal is to keep this pretty inexpensive. If we had piles and piles of money, the problem would be a lot easier to solve. Even with low cost, we want high quality, and we have kind of a unique 3D reconstruction of these bugs. That's the most bugs I think we've ever been talked about in the building, by the way. So we need to be able to capture these images in order to support the 3D reconstructions as well as label data capture. So I think everybody knows the GigaPan solution. It's fairly good. We've also looked at lasers, optical structured light kinds of cameras. They all have benefits and drawbacks, but primarily most are fairly expensive. Excuse me. So in thinking about this should be really easy. You just move a camera around precisely, take a lot of images, and let software do the rest. So I had the idea to put a camera on a CNC machine. A CNC machine is a computerized, usually with a tool head on it, computerized machine that can machine parts. They're fairly well known. They're tried and true technology in the machining world. So why not take that, attach a camera with a pan tilt head on it, program it, and let it run, and we've got everything, right? Should be easy. So CNC machines are these fairly big beasts. The lower one is a little bit smaller. Those are fairly inexpensive. So if we were doing very small specimens or small trays, the smaller versions are fairly cheap. But once you get above about a square foot, the price jumps significantly. There are some do-it-yourself kits available of various quality and various pricing. Before I went to go and build a machine myself, I really wanted to get a commercial machine and try it. Because if I build a machine and it doesn't work, or it's inaccurate or something's wrong with it, I'm not sure if it's me, the machine, what's wrong. So the machine that's upstairs is a factory machine, not a do-it-yourselfer, although it's got some do-it-yourself parts on it. So some things to consider when putting this whole thing together. Obviously imaging, the workflow integration. We're only as good as the images we capture. So we need to use as high quality of a sensor, high quality of a lens as we can, given the cost constraints we're under. And I put lighting last. Lighting is crucial to any imaging application. And I know some of you probably have more experience than I do, and I'd love to talk to you about lighting. So on the software side, we have stitching software, which takes takes all of these individual images and puts them together into one. We're working around 600 megapixels now for the trays. I think that would be a great discussion to have as well. What is the right resolution to be capturing these at? Or what are the upper and lower bounds that we want to be looking at? We have a 3D reference algorithm that we have running. It's a little bit slow, but we're working on that in conjunction with the Parallelism Center to speed that up. And I guess there is this whole issue of machine control and programming the thing, and as well as the workflow. That's got to be as automated as possible and easy to use, so we can have hourly kind of people come and run the trays through the machines. So this is actually a picture of the machine that's upstairs right now. It's an industrial 3-axis CNC machine. It's got a fairly large bed because we're taking off-axis shots. We need to get outside of the tray, so we needed to make sure we had enough room to do that. The camera that we're using is an industrial camera. If you can see the small white block there, that's basically the entire camera. It's just a sensor with a USB port on it, and everything else is done through the computer. We're using a telecentric lens, which takes a parallel projection of the image onto the sensor, so there are no perspective distortions, and measurement. It's much more accurate if you're going to do measuring with any of these images. Then we use a servo-controlled pan tilt mechanism, which is not really visible in the picture because it's behind the camera, but rotates, pans, and tilts the camera. And the industrial-looking steel there is something that I fudged up in my garage. I shouldn't have said fudge. But yeah. So we got the machine last week. So I kind of put it together and tried to make everything run on short order. I built that frame to mount everything to the machine just on Thursday. So these are very preliminary experiences. The thing works. You can drive it around. You can take grids of pictures. There are quite a few little gotchas. The machine program runs in old versions of development tools, and so trying to glue everything together is a little bit of a challenge, but that's just going to take some time. And I tried to build this mount in a way that we could adjust it up or down, back and forth, so we can get the camera far enough away from the machine so we're not getting lighting issues. And we have the machine has a 6-inch vertical travel, so if we were going to do any focal stacking or depth of field, we have depth of field problems, we need to have the camera in the right position. So it's somewhat adjustable if you get into the steel with some wrenches and cut your knuckles. So I guess a few comments. This thing weighs 450 pounds. It's a big machine. They were for the shipping department here. Servers used to be big things, but servers, one person could pick up a server nowadays. But it took a small team of people and a few phone calls to get this thing up on the stand. The vendor who we got this from in Chippewa Falls, Wisconsin, was very good on the phone, but in terms of tech support and development support, they were supposed to build the camera mount and other things for us. So I ended up having to do a lot of this stuff myself. So I think they're motivated to sell a handful of machines, but not much else. And because this machine is so large, it doesn't look so large in the picture, but when you get near it, I mean, those blue things are a foot wide. It's really a challenge, and this thing is moving up and down and back and forth. It's really a challenge to get light onto the specimens and keep it there. I'd originally experimented with lighting that was attached to the front of the lens, but that becomes a problem because shadows are cast differently depending on what angle you're taking the picture at, and so the feature matching and the stitching code and then the 3D reconstruction code can be thrown off by those. And it didn't work very well either. So what's next? I think I'll show, when we go upstairs, I'll show some, we can look through the camera and see what it's seeing. It's not nearly the quality that I expected, and so I need to talk to the engineers who recommended that and work with them. I think it will get better, but I'd like to use some other cameras that we know as a known reference point. So we have the machine, we can put anything on it and just let it run. You press a button and it just goes, and you can come back when it's done. Yeah, we just, my goal is just capture as many images as possible while we have this thing. We still don't understand what are the optimal angles for getting into the label data under the specimens, and what are the proper angles and azimuths to do the 3D reconstruction. So the more experimental data we have, the better off we'll be. My handiwork mounting block is a little bit flimsy. I engineered it as good as I could with hardware store style things, but the camera does shake a little bit, which means we have to wait for it to stop. We really need a proper mounting block for that. And all of this needs to be integrated with the web workflows. So this will all be run from the website. You'll log in, and all your collections data will be there. We have, well, that's not quite ready yet, and we need to deal with, since we're here and operators may be anywhere, there could be capture issues, stitching issues. I think we're kind of concerned that there might be network issues and uploads. So what happens if you take 120 images, you're trying to upload them, and the 99th one dies? You have to resend them all. Is the whole thing wasted? We don't want to waste any work. And we really need to field test this. It's one thing to have it upstairs here, but I know I've talked to some people about bringing some things over and working with it. So beyond that, that's the CNC version. I've been working with a local robotics engineer who's got a ton of experience. I knew nothing about robots before I started all this, which I think is somewhat of an advantage because I don't know what I can't do. So, but the next machine that we're looking at, primarily because of the lighting issues of this big CNC machine moving back and forth, is called a parallel robot. And this is a machine where all the hardware is up high and just have some arms that come down. So you can see from those images that if those were specimens there, they're going to be much easier to light than, and in fact, the lighting can be integrated into the frame of this machine. And these are videos which I'll show you, although when I showed it to Chris, he had a moment. So John calls it the bug scrambler. So I'll show you the bug scrambler here. If it goes. I might have to, I have them on the desktop. So these are primarily industrial kinds of robots.
Now, oh, this thing, that's about it.
So they're very accurate
I think there's
and very fast.
discussing it with him on Sunday. I think there's a fundamental,
Sorry about
I like to say software because I'm not a software guy.
No, it's kind of fun to hear the vacuum picking things up.
Thanks, Ruth. That's a good thing I'm recording our sound here. He's using, ruthless.
These are used in production lines, assembly lines, pharmaceuticals for picking things, putting candy in wrappers and other things like that. So the idea would be to use this not run it nearly as fast. But I just showed that so you can see what it's capable of. This, I believe, is the actual design of the machine that I have all of the design plans and parts lists and other things for. It can pick up about 5 kilograms, and that's probably a more reasonable motion speed. Something we're more likely to use rather than shuffling ping pong balls. Oh, you can't see, but on this machine, this machine has 4 arms rather than 3, so it can actually articulate that plate on the bottom in any direction. So that's really useful for getting the 3D. And I'm not sure if we're going to need to actually pan the camera, or if we can articulate it properly such that we just need to rotate the image, which I think we'll be able to do, rather than have this extra pan tilt hardware, which just complicates things more. Sorry. Okay, so the nice thing about these are much fewer moving parts, much smaller machine. A lot of the CNC machines' size and mass is there to just maintain rigidity as one part moves across the other. I mean, they're also meant for machining things like aluminum and steel, so whereas these are more for picking things up and moving them around. And yeah, less lighting interference. So that's what we'll be doing next, and that's the end.